In this last video for section 4.1, we're going to look at an example of a subspace. So before you watch this video, please make sure that you've read over the definition of a subspace in the learning module or in your textbook. So the set that I'm going to look at here in the example is going to be called Pn, so P with a subscript n, and it's the set of real polynomial functions of degree at most n. So let's work through what that means. That means if I have some element of this set of polynomial functions, then this is what that function is going to look like. It's going to look like a polynomial, and the degree of it is at most n. So I know there isn't an x to the n plus 1 term, or an x to the n plus 2, and so on and so forth. This has to be the largest power of x that appears in my polynomial. Now this coefficient, this a sub n, could be 0. It could be that the degree is less than n, but this is the highest that it can be. And what we want to do now is show that Pn, this set of polynomials, is actually a subspace of V. And V is the set that we met in the first video from this section, the functions from the real numbers back to the real numbers. And if you've read the slide for subspaces, then you know that there's two things we have to do if we want to show that our set is a subspace. We have to show that it's closed under addition and closed under scalar multiplication. And let's just do those one by one. So first up is closure under addition. And in order to show that my set is closed under addition, I have to start with two elements of my set. So two polynomials of degree at most n. And this is the notation that we have to use because I don't know what my coefficients are. I just have to give them names. But I know that the highest power of x is n, and then we can have any other powers of x below it. And I've just used these two different letters with subscripts to represent the coefficients on each power. Okay, so now let's add these two functions together. Let's look at p plus q. So going back to the definition of adding functions, what this means is that when I plug in a number, that number just gets plugged into both functions separately, and we add that together. So if we plug it into p, then we get this whole expression. We can add some parentheses around here, make this a little bit more clear what's going on. So this first set of parentheses is just the function p, and this second set of parentheses is from q. But now what I want to do is collect terms. So I have an an times x to the n and a bn times x to the n. But what I want to do is combine those two together to get one single term. So this is really an plus bn times x to the n power. So I've just collected those two terms. And then you would go to the next one, the x to the n minus 1 term, and you would want to collect those two coefficients, like I did here. And then you would just keep on going through, collecting all of your coefficients for corresponding powers, and your last term would be your constants, so just tag those on the end, a0 plus b0. And the form of what we've ended up with here is another polynomial of degree at most n, because, well, we can see exactly what it is. We have x2 powers, and the largest power is n. So that completes addition. We added our two polynomials. We ended up with another polynomial. So to finish off, we'll look at closure under scalar multiplication. So what that means is I need to take a polynomial like p and multiply it by a scalar In this case, I'm calling my scalar c. So when I plug in to this new function c times p, we of course plug x into the function p, this polynomial, and then multiply by c. So I've just written out my polynomial again from before, and then written c on the outside of the parentheses to show that it needs to be multiplied through, distributed. So each term over here is going to get multiplied by c. So we actually have c times an times x to the n power plus c times an minus 1 times x to the n minus 1 power, and so on and so forth. And then the constant also gets multiplied by c, and we'll stop there. So the form of this new function is also a polynomial of degree at most n. And that finishes off the proof. Once we've shown that it's closed under addition and scalar multiplication, that's all we have to do to show that this set is a subspace of our original vector space of functions from the real numbers to the real numbers.